Welcome to the session, Rainwater, the Emerging Alternative Water Source. I'm Tamim Younos, and I'm with the Green Water Infrastructure Academy, and I am also serving on the ARCSA Foundation Board. So the purpose of my talk is to set the agenda for this session, and so we start from here. Okay, this is one of my most favorite slides, which shows land development in the eastern United States around DC area from 1792 to 1992, about for over 200 years. So, and this slide ends actually in 1992, so all those gaps are filled, so the area is totally filled with land development and populations getting higher and higher. So I just wanted to show you the emergence of population centers in the United States, but it's not unique to the East Coast. So there are a lot of urban centers or population centers across the United States. As this map shows, about over 80% of the US population live in these urban areas. And also I should mention that about 50% of the population live in coastal areas. So these are the highly urbanized areas, which of course need a lot of water and need a lot of energy. So going to the 20th century, so the centralized water infrastructure started in the early 20th century, and it was a marvelous system. We call it modern urban water infrastructure, which basically has got three systems within it. Potable water system, which is drinking water system. It includes water source development, water treatment plants, and water distribution systems. And then we have wastewater network, which is wastewater collection and drainage, wastewater treatment plants, discharge to surface waters. And finally, most important is also stormwater or runoff drainage network, which basically the stormwater runoff is collected from impervious areas and stored in disposed surface waters. And there are two ways to do that: combined sewer systems, which sewers and stormwater were combined. And there are only a few systems which operate with CSS right now. And then MS4 which is very common now, which is municipal separate sewer stormwater system. So they flow in different pipelines. So centralized water infrastructure, they brought a lot of good things to urban areas and a lot of healthy life. But now if you are entering the 21st century right now, so we see the aging of these infrastructure, which is a lot of breakdown and leakage. And we see water scarcity and flood in urban areas. And we see the need to adapt to climate change and extreme weather conditions. And we see energy intensive water infrastructure. And we see cybersecurity issues, which relates especially to centralized drinking water infrastructure. So the modern water infrastructure, which were designed in 20th century, is kind of not meeting the goals of 21st century. So we have to think what we are going to do now. To just summarize the 21st century challenges in urban areas, I have 4 bullets here. This is not the whole thing, but I just bring up the important stuff. Water demand and scarcity, urban flooding, energy demand for water sector, and water and energy demand for food security. These are the challenges that we are facing in urban areas today. So to cope with the 21st century challenges that we saw in the previous slide, so there's the need for developing novel holistic approaches that integrates natural and engineered systems into planning and design of urban water infrastructure systems, solutions that recognize the nexus between water, energy, and food production in urban environments. So this is the way we are going to cope with the problems. So this diagram shows the transition to 21st century ingredients or elements for holistic approach. So here we have science and technology, and here we have policy and regulations. So no doubt there are significant advances in science and technology, and things are happening all across the United States and around the world. But we are kind of facing problems with policy and regulations. We are facing problems with education, and we are facing problem with practice, how to like use the science and technology to design systems which are coping with 21st century problems. And also we have a great problem with public perception that's there. So these are like the elements that we are going to deal with when we transit to 21st century. The other important diagram which I want to show to you is food, water, energy nexus in urban environments. Nowadays it's called FEW. So you see here, like we have the food, which is totally, food production totally depends on water and energy. On the other hand, water depends on energy, water production depends on energy, and energy production depends on water, so they depend on each other. So all these three are very important in urban areas where we consume a lot of water, we consume a lot of energy, and we consume a lot of food. Here in the middle, I have holistic and sustainable and green systems. So this is the new approach we are thinking about. And green systems means also like urban agriculture and food production within the urban areas. So from centralized systems, we are moving to decentralized water infrastructure. And basically, these are smaller scale water management and water infrastructure systems, which are not centralized. So we can have smaller scale, we have it localized. Here is the vision for a future. If you see here, we show decentralized water infrastructure, which has got several components. And if you see rainfall, like we collect the rainwater harvesting is one component. We have porous pavement, for example. That's another component of this decentralized system. We could have here like rain gardens, another component. Urban ag, like we could grow food around here and other things. So this is the kind of the water component of it. And also this area, or like this building and these paved areas, produces wastewater and also stormwater runoff. So the vision is that we have a decentralized or smaller scale advanced water system, treatment system nearby, that we treat wastewater and we treat the stormwater, and we return it back, the treated water is returned back and used inside or outside the building. So normally water treatment is energy intensive. So the idea is also to use locally available energy, renewable energy, such as solar in this case, to treat this water and deliver it back for use to the building or surrounding areas. So basically, this is the vision which partially is happening, but still we are not there. So functions and advantages of decentralized water infrastructure. It enhances the potential for using locally available alternative water sources. The focus is on alternative water source. Alternative means it's not the surface water, it's not the groundwater. So it is probably rainwater, stormwater runoff, and maybe saline water, which is brackish water, salt water, or wastewater. These are alternative water sources. The other major element is energy conservation. When we are using centralized systems, we bring the water from remote areas. So we use a lot of pumps, for example, and we use a lot of energy. So the potable water systems for centralized systems are very energy intensive. But with decentralized systems, since we are trying to use the local energy sources, so we save a lot of energy there. And also with smaller system at present, there's more potential to use locally available renewable energy sources, as I showed you the solar PV in the previous slide, to use that for water treatment and also use it for in-building water distribution. And then also decentralized system enhances cybersecurity. If you are watching the news, centralized drinking water systems are under attack. And so the larger population, there's larger risk. And centralized systems, like sometimes they serve thousands and millions of people. But with smaller system, we serve smaller number of people. So cybersecurity a little bit more safe for decentralized system. So as we know, the topic of our talk today is rainwater harvesting. And rainwater harvesting is a major component of decentralized system, which has other elements too. And within the rainwater harvesting system, there are two major branches. One is rooftop rainwater capture and use. The other was in stormwater runoff capture and use. So basically, as we see, rainwater harvesting systems mitigates the 21st century challenges in urban areas. It deals with water scarcity, it deals with flood control, it deals with energy conservation, and food security. And these are kind of all advantages of rainwater harvesting systems. So here in the left, we show rainwater uses, on the right, benefits. So all these uses bring different types of benefits. Like indoor uses, rainwater is used for non-potable uses such as flushing toilets and cooling and that sort of thing, which is becoming common nowadays, but not as common as we'd like to see it. So if we use rainwater for indoor uses and also outdoor uses, which is shown here, lawn irrigation and car wash gardening, so it facilitates water resource conservation. So this amount of water we do not bring from surface water, but we use rainwater. So normally about at least 2/3 of potable water is used for these purposes that could be used instead. The rainwater could be used instead of that. So emerging uses, potable water, urban agriculture, groundwater recharge, and urban aesthetics. Potable water, of course, rainwater is used for drinking purposes for centuries, but here we are talking about larger scale commercial buildings and that sort of thing, a larger scale of rainwater use comparing to a very small household, which they use rainwater already in many places. And also urban agriculture, we use rainwater a lot in our backyard gardens, very small scale, but urban agriculture means a little larger scale in food production in urban areas. Groundwater recharge and these two other practices are happening, but are not very common. But our focus today is in these emerging potable water use in urban agriculture. So, and also you see here, like other than saving water, it's effective. Rainwater harvesting is effective for stormwater management and flood control. And as we talked, it facilitates energy conservation. So this is a simple diagram. We see that 1,000 square feet of rooftop captures 620 gallons of rainwater per 1 inch of rainwater. So in a place, say for example in Virginia, where I am, like the average annual rainfall could be 41 to 43, in some places 46 inches. So this 1,000 square feet will collect 620 times 41 inches. So this one fact in terms of quantity of available rainwater. The other one here, rooftop areas constitute 30 to 40% of impervious areas in urban settings. So as we said, we have two types of impervious areas, paved areas like roads and parking lots, and rooftops. So rooftops are 30 to 40%. And our talk today mainly relates to rooftop rainwater applications. So to give you an example, this is Hampton Roads, Virginia, and I want to show you the rainwater as potential water source or alternative water source. Hampton Roads is by the Chesapeake Bay. It's called Hampton Roads, but it includes like Newport News and Norfolk and Virginia Beach and all other cities. So it's a number of cities. Also, there's a place Hampton called too. So it's a large area which uses a lot of water, and a lot of the James River and other rivers, Elizabeth River in the area, which like flow to the Chesapeake Bay. So estimated urban stormwater runoff from Hampton Roads. So here are picked up only 3 cities. If you see, for example, for Norfolk, 1,250 million gallons of stormwater runoff could be collected from impervious areas. For Hampton Roads, for total, which is includes some other cities here, 12,563 million gallons of stormwater runoff, which right now it flows to the rivers and the Chesapeake Bay. And actually, some studies show this is also a reason for a little bit of sea level rise or ocean water level rise in the area, because we get so much stormwater runoff there. So here I used that impervious area total runoff from the previous slide, and took the 30% of that, because rooftops is about with the lower estimate, rooftop is 30% of the area in these cities. So in Hampton Roads, so actually from rooftop, we can collect 3,769 million gallons of water per year. And these numbers shows for the 3 cities. So to summarize this, in Hampton Roads, Virginia, stormwater runoff produces 12,563 million gallons of water per year, and rooftop rainwater, 3,769 million gallons per year. So since we are not using this water, it goes to the rivers and the Chesapeake Bay. So I call these wasted waters, which actually has got a lot of potential. So goals of today's session is discuss cutting-edge topics in rainwater harvesting. Rainwater harvesting for potable use, as I said, it applies to commercial buildings, and rainwater use in urban agriculture, which relates to food security. And of course, cost is a major issue. So life cycle assessment of rainwater harvesting system is a major issue that some researchers working on. So here I want to introduce our speakers. Our first speaker, Dr. Philip Thompson. He's a professor of civil and environmental engineering, University of Seattle. You can see his bio on our website, ARCSA website. He has done a lot of studies on water treatment and potable water systems and environmental justice, all sorts of things. So, but today he will talk about use of rainwater for potable purposes. Dr. Tamim Younos. She's an assistant professor of geography at Colorado Mesa University, and she is an expert in geospatial analysis. And when we talk about urban agriculture, that will be the subject of our talk, geospatial analysis becomes critical, because basically with geospatial analysis, we can identify the roof areas, we can identify the potential for urban agriculture, we can calculate the amount of rainwater available and everything. So Dr. Tamim Younos will talk on that subject. And here then we have Dr. Santosh Gimar, and he's an interdisciplinary environmental engineer and scientist with the US EPA Office of Research and Development. And he's worked for many years on life cycle assessment issues, including rainwater harvesting systems that only a few people work on. So this session, as I'm talking, is recorded, but then probably in the middle, we might have some time for, after each recording, a couple of minutes for question and answer. But basically, toward the end, we at least will have 15, 20 minutes or more to be interactively involved with you, the audience. And that session is moderated by Alena Armel, professional engineer who is a project manager with water resource engineer at AECOM. So Alena will give you the opportunity to interact, and so you should, when you are watching this, please make notes of your questions and everything. So Alena will collect that and respond to your questions. So saying all that, so please welcome our speakers, and let's get started with the session. The rainwater, the emerging alternative water source. Thank you very much. And now we go to session speakers. Thank you.